So after discussing about intensity, now it is time to discuss about radiation pressure. Radiation pressure or radiation force. Talk about force also. What is this? Radiation pressure, radiation force. So by now we have learned the radiation. For example, light is also radiation, electromagnetic radiation. It has two properties. It can behave like wave or it can behave like particle. Okay, so since a radiation can behave like particle, we call it photon. We call it as photon, and this photon has got momentum. So this photon, when it strikes on a surface or strikes on a body, this photon is capable of exerting a force on the body. Understood? So let us discuss this force per unit area will be called as pressure. So this is radiation force or radiation pressure. We have learned in class 11 in laws of motions. Okay, if there is a surface, there is a wall. On this wall, a body of mass m moving at a velocity v strikes. Okay, so here initial momentum, we call it as mv. I'll avoid a minus sign. And suppose after striking the wall, the body comes to rest. That means it got stuck up on the wall. Then final momentum will become how much? 0. So this is a change in momentum. Change in momentum. Okay, how much is the change in momentum? Final minus initial. It is minus mv. Let me avoid a minus sign. There is a change in momentum is what? mv. Similarly, if the body of mass m is striking the wall with a velocity v, and rebounding elastically means with the same magnitude of velocity, with the same kinetic energy in the opposite direction, with the same speed, opposite direction. Then initial momentum is mv, if we call it as, then final momentum I have to call it as minus mv. So change in momentum is what? Minus twice mv. Okay. So if this is the change in momentum, then we understand the change in momentum per second. For example, in this situation, if every second, suppose n balls are striking, how many balls? N balls. Every second, how many balls are striking? N balls are striking. Then every second, and change in momentum of each ball is how much? mv in this first situation, when the ball gets stuck up after striking, right? So every second n ball is hitting, and change in momentum of each ball is how much? mv. So change in momentum of n balls will become how much? n mv. And here n is the number of ball hitting the wall every second. Then what will be the force? Force will become change in momentum every second. How much is that? What is that? n mv. This is the change in momentum every second, because n is the number of particles hitting the wall every second. Otherwise you can understand it like this. On this particular wall, suppose n balls hits in time t. Each ball of mass m hitting the wall with a velocity v, and after striking it is coming to rest. Means getting stuck up with the surface. And how many balls getting hit? N balls. For one ball, what is the change in momentum? mv. For n balls, what is the change in momentum? nmv. So this is a total change in momentum. In how much time? In a time of t, because n balls are striking in a time of t. So therefore, what will be the force? Force will become change in momentum divided by time taken. So nmv divided by time taken. So if we have to calculate, n by t is the number of ball striking the wall per second. Let me call it as small n. So small n mv. This is how we calculate. So in this situation, ball is hitting and reflecting with the same magnitude of velocity in the opposite direction. So here also, if n balls are hitting the wall every second, then here change in momentum every second. Change in momentum every second will become how much? n into twice mv. Twice mv. That is twice n mv in these situations, because here change in momentum is twice mv, and the first situation change in momentum is mv. Okay. In a similar manner, let us understand the radiation pressure. In a similar manner, let us understand the radiation pressure. So let us consider a surface on which intensity light, on which light is falling or radiation is falling. Radiation is falling. And let us assume the intensity of this radiation is I. I be the intensity. Okay, that is energy falling per unit area per unit time. Falling per unit area, energy falling per unit area per unit time. Let me consider the area of the surface to be A. A is the area of the surface. Then we call it as intensity, total energy by total area by total time. Then from here we get one thing, energy falling every second is what? Intensity into area. This is the amount of energy falling every second. This is the amount of energy falling every second. So energy received by the surface, energy received by the surface every second is how much? Intensity into area. Okay. If EP, the energy, be the photon energy means photon energy, that means energy of each photon. Then number of photons striking the surface, number of photons striking the surface or falling on the surface per second will become how much? Okay, total energy falling per second divided by energy of each photon. And we know the energy of the photon. How much? I can write h nu or hc by lambda. Okay. This is going to be the number of photons. Let me represent it by small n. Number of photons falling on the surface per second. Now for this particular surface, one more thing here. So what will be the force here? Now the force will be defined as what? Force will be defined as a rate of change of momentum or total change in momentum divided by total time taken. Total change in momentum divided by total time taken. And from here we will define pressure. How pressure will be defined as? Force divided by area. That means 1 by area delta P by delta T. Okay. So this is pressure. Now one thing out here, let me define few quantity for this particular surface. Let me assume for this particular surface exactly what happens when radiation is falling on a particular surface. Three things may happen. One is a part of it may get reflected, a part may get absorbed, and a part may get transmitted. One part is getting reflected, one part is getting absorbed, and one part is getting transmitted. Though we will not be considering the transmission part out here, we will be considering only reflection and absorption part. Then here there will be three quantities. One is your reflection coefficient, one is your absorption coefficient, and the other is your transmission coefficient. Transmission coefficients. They are defined as absorption, reflection coefficient R, absorption coefficients A, and transmission coefficient T. What is this exactly? Let me quickly understand it. You have learned these things already in heat and thermodynamics in heat chapter, probably in class 11, right? So here what is happening? Suppose a certain amount of light, suppose 10 is falling on the surface, and out of 10, suppose the amount of light which is getting reflected is 3, and the light which is getting absorbed is, suppose, your 5, and the light which is getting transmitted is your 2. That means how much is falling? 3. So now reflection coefficient will be defined as amount of light which got, amount of radiation that got reflected by amount of radiation, total radiation which was incident. This ratio will be defined as reflection coefficient. That means how much got reflected? 3 out of how much? 10. So 3 by 10 will be reflection coefficient. Similarly, what is absorption? How much got absorbed? 5 out of how much? 10. That means 50%. That is half got absorbed. So absorption coefficient is half. How much got transmitted? 2 got transmitted. Although how much? 10. That means 1 by 5. This will be defined as transmission coefficient or transmittance. For this is reflectance and it can be also called as absorptance. Right? So these 3 quantities there. Now for this particular surface on which light is falling having intensity I, for this particular surface we will be considering only R and A. Will not be considering transmission. Okay, will not be considering transmissions. Now let us consider case 1. Let us consider a surface which is perfectly absorbing. What surface? Perfectly absorbing surface. Perfectly absorbing surface. That means whatever falls, everything will get absorbed, nothing will get reflected. So in this situation, what will happen? Absorption coefficient will become equal to 1. Everything got absorbed. That means 10 out of 10. 10 divided by 10 got absorbed. How much got reflected? 0 out of 10. Nothing got reflected. For example, reflectance coefficient will become 0. In this situation, what will happen? You see. Okay. The photon which is falling, on the surface. Let me consider the surface here again. The photon which is falling, a single photon which is falling on the surface, it is falling with a momentum h by a lambda. So this is initial momentum. Okay, momentum initial how much of the photon? H by lambda. After falling, got absorbed. So what is the final momentum of the photon? 0. So what is the change in momentum of the photon? Final minus initial, h by lambda. I am considering the magnitude only. Minus sign I am not considering. We can avoid it for understanding the concept. Okay. So this is the change in momentum of. This is what? Change in momentum of one photon. Okay. So therefore, if number of photons hitting on the surface every second is n. Okay. If number of photons, this is n beta photons striking the surface every second, then what will be the change in momentum every second? Then therefore change in momentum every second will become how much? Change in momentum of one photon, h by lambda. For n photons, n h by lambda. This is a change in momentum every second because this is a number of photons striking every second, and this is the change of momentum of one photon. So total change in momentum every second is nh by lambda. And we understand the change in momentum every second. This is what we define it as force. Okay. Now how much was n? We have already done n. N was how much? I a lambda by hc, h by lambda, lambda cancel, h is cancels. How much is left up with? I a by c. So this is force. I intensity area by force. So this intensity into area can be called as incident power on the surface. Okay, incident power on the surface. But this is not the power of the source. Keep it in mind. This is not the power of the source. Okay, power of the source is somewhere else. Okay, but on this particular surface, how much energy is falling every second? Okay. We have written earlier also energy. We have written earlier also energy by time is equal to area into intensity. This is energy part. So it can be called as incident radiation power. We can call it as power also, right? But not power of the source. Power of the surface. Radiation power on the surface. So this is what exactly is your force. So this force, if you divide it by area, so this is going to be your pressure. So pressure is going to be your force divided by area. So how much is that? I by C. So this is the pressure exerted by the radiation on the surface. Okay. If the surface is perfectly absorbing surface. Okay. So this is the force the photons is exerting on the surface in the downward direction. And this is also the force exerted by the surface on the photons in the upward direction, because every action has equal and opposite reactions. You know it very well, right? Okay. So this is force, one is action, the other is reaction. So magnitude of force on by photon on the surface, IA by C, or by surface on the photon is IA by C in opposite directions. So this is the first case for perfectly absorbing surface. Similarly, if we consider a perfectly reflecting surface, that means photon is falling with momentum h by lambda, photon is getting reflected with the same magnitude of momentum in the opposite direction. So initial momentum h by lambda, suppose downward direction, final momentum h by lambda, suppose in the upward direction. So change in momentum of one photon, how much is that? Final minus initial. Since they're in opposite direction, when you subtract, you will get twice h by lambda. Now if n photons, how many photons are hitting the surface every second? How many photons? N photons are hitting the surface every second. Then change in momentum, that is force, will become how much? Okay, n into change in momentum of one photon, that is twice h by lambda. I hope you have got it right. Okay, I don't think there should be any problem here. N photon, the change in momentum of one photon, twice h by lambda. And how many photons are falling? N photons are falling every second. This is the number of photons falling every second. So change in momentum every second is what? N into twice h by lambda. So change in momentum every second, we can define it as force. So n was how much? I a lambda by hc, and twice h by lambda, h is cancels, lambda cancels, twice I a by c, this is force, therefore pressure will become force divided by area. If I bring area to the left hand side, how much will remain? Twice I by c. So this is the radiation pressure on a surface which is perfectly reflecting. I hope you have understood it well, right? Again, force exerted by the photons on the surface will be in the downward direction, and force exerted by the surface on the photons will be in the upward directions. Okay, that is the difference. Now third situations, we'll be considering a surface from where a part will get reflected and a part will get absorbed. How to discuss that particular point? This is the last point, case 3. Third case, this was the case 2, this was the case 2, it is the case 3. Okay, the case 3. This is when a part of radiation is absorbed. When a part is absorbed and a part is reflected. So here I forgot to mention one point. Everything is getting reflected, nothing is getting absorbed. So therefore absorption coefficient will become 0, reflection coefficient will become 1 in these situations. Everything is 10 is falling, then 10 is getting reflected. So 10 out of 10, 1. Okay, 0 out of 10, nothing is getting absorbed. So absorption coefficient is 0. But in this situation, when a part is getting absorbed, not everything, so something is getting absorbed, so absorption coefficient will become greater than 0 but less than 1. Similarly, reflection coefficient will become greater than 0 but less than 1. But one thing you need to understand, A plus R is equal to 1. A plus R is equal to 1. Okay. For example, 10 is falling. Out of 10, 4 is getting reflected and 6 is getting absorbed. So then absorption coefficient will become 6 by 10 and reflection coefficient will become 4 by 10. So if we add A plus R, how much is that? 10 by 10, that is equal to 1. Okay, 100%. So now here we'll discuss it like in this way. First thing, let us talk about the reflected photon. Let us talk about the reflected photon. So we know from the previous discussions, the change in momentum of one reflected photon. How many? One reflected photon. Reflected photon. How much will become that? Twice h by lambda. Okay, and change in momentum of one absorbed photon. How much is that? H by lambda. Keep that in mind. Okay, change in momentum of one reflected photon, twice h by lambda, and change in momentum of one absorbed photon, h by c, h by c. Okay, now number of photons incident every second, that is per second, is equal to suppose small n. Okay, number of photons incident per second is what? Small n, which we already have the expressions, we have already got it. This one, number of photons striking per second, IA lambda by hc, that is IA lambda by hc. This is the number of photons incident per second. So therefore, number of photons reflected, how to calculate it now? Reflected per second, how to calculate it? How to do that? N into R. Not understood? Let me show an example. Let me show it in example. Okay. For example, for this particular surface, reflection coefficient is suppose 2/3. Reflection coefficient is suppose 2/3. That means 2 part will have to get reflected out of 3 part. That means if 30 photon is falling, that means how many will have to get reflected? 2 part out of 3 part. So 2 part means 20 will have to get reflected. So how will you get 20? Number of photons getting reflected is equal to number of photons falling multiplied by R. That is 30 into 2 by 3. How much is that? 20. Understood? Okay. So therefore, number of photons getting reflected is what? N into R. How much is N? This is N. IA lambda by hc into R. Similarly, number of photons absorbed will become how much? N into A. IA lambda by hc into A. Okay. But we can write it like this also. IA lambda by hc. A can be written as 1 minus R, or R can be written as 1 minus A, whichever way it is convenient for you. Right? So this is the number of photons getting reflected per second, and this is the number of photons getting absorbed per second. Okay. So therefore, force on the plate due to which one? Reflected, due to reflected photon. We understand due to reflected photon, change in momentum of one photon is what? Twice h by lambda. And in this situation, how many photons are falling? How many photons are getting reflected? Reflected photon is how much? This is the reflected photon. IA lambda by hc into R. This is the number of photons getting reflected every second. And change in momentum of one photon which is getting reflected is what? Twice h by lambda. Similarly, force on the plate due to absorbed photon, AB, SORBD, absorbed photon. Okay, photon is incident getting absorbed. So change in momentum is how much? H by lambda for absorbed photon. Okay, so how many photons are getting absorbed every second? IA lambda by hc. I can write it as 1 minus R. And changing, this is the number of photons getting absorbed every second, and momentum of one photon is what? H by lambda. So here what you get, hs you can cancel, lambda you can cancel. You can write it I A R by C. There's a 2 in front of it. H getting cancels, lambda getting cancels. I A C by 1 minus R. So force on the plate due to reflected photon. This is due to reflected photon, and this is the force due to the absorbed photon. So what will be the total force now? Then force is what? Sum of both the forces, because the both the photons are going to exert a force on the surface in a downward direction only. So therefore net force is going to be force due to the reflected plus force due to the absorbed. That is force due to the reflected twice AR by C plus IA by C 1 minus R. So how much will get here? 2 minus 1 is 1 plus 1. Okay. So finally how much will get? Let me take common. This is, I made a mistake here. Just a minute. Sorry. IA by C twice IA R by C. This is R. So R only, correct only. No problem. Correct only. So here I A by C, you can take it common. Twice R, that will become twice R plus 1 minus R, that is IA by C 1 plus R. Okay, this is the force on a surface when the surface is having a reflection coefficient of R. You can replace R, you can replace it by 1 minus A also. You will get in the expression in terms of absorption coefficient. Therefore, in this situation, radiation pressure, let me use pressure. Radiation pressure, force divided by area, that is I by C 1 plus R. So this is in general expressions. So from here we can get the previous two equations. Okay, how? For a perfectly reflecting surface, reflecting, everything will get reflected. For perfectly reflecting surface, R is equal to 1. So therefore pressure will become how much? 1 plus 1 is 2, twice I by C. This is for perfectly reflecting surface. Similarly, if the surface is perfectly absorbing, R will become 0. R will become 0. So perfectly absorbing surface, it will become I by C, perfectly absorbing surface. Okay, so I hope you have understood it. Okay. Thank you.